So, hello everyone, welcome back to our channel and welcome to the second and final session of our robotics series where we will go deeper into mechanical design and CAD and we will focus on turning a reference robot into something more refined, more reliable and more competition ready today. By the end of the session, uh, I would suggest that you should see how mechanics, electronics, and control systems all come together in relevant robot. So yesterday we have go through the UI of the Onshape with the help of our teammates Aravi and Darsh. I would like to hand over the mic and the things to the team.
Hello everyone, this is REV from Team Kaizen. I'm joined with my teammate Tarsh, who is also from Team Kaizen. And today, as Mr. Sahil said, we'll be covering everything we did yesterday, where we just introduced the UI, but we'll be going into more details about everything. Uh, so, Yesterday we covered CAD using Onshape, 3D printing using Cura, programming using picto blocks, and assembly. So you saw what CAD looks like, how simple shapes are created, and how those shapes can turn into real physical objects with 3D printing. You also got an overview of how robotic systems are designed and how different components come together, but that was just the surface. Today we're going to go deeper. This session is not just about learning how to use a specific software. It's not just about memorizing where the buttons are or the following steps without understanding them. Instead, the goal today is to understand how and why things work the way they do. When you use any CAD software, whether it's beginner tools or more advanced platforms like Onshape, you're not just drawing shapes, you're defining geometry with precision. You're controlling dimensions, relationships, and constraints. Every line, every circle, every feature you create is based on logic, not just guessing. So today we're going to focus on three key ideas. First, parametric design. This means that instead of drawing something once and leaving it fixed, you define it using dimensions and relationships. If you change one value, the entire model updates. This is how real engineering design works. It's flexible, adjustable, and controlled. Second, we're going to focus on design intent. When you create a model, you're not just making it look correct, you're deciding how it should behave when changes are made. For example, if you increase size of a part, should the holes move with it? Should certain features stay centered? Should proportions remain constant? These decisions define whether a design is robust or fragile. Third, we'll focus on precision and constraints. In beginner work, it's easy to place things visually and say this looks fine. When real design, that approach fails quickly. Instead, everything must be defined. Exact distances, exact diameters, and exact alignments. Constraints are what lock your design into a predictable and a reliable structure. We're also going to connect this directly to real world applications. The parts we design are not just digital models, they are intended to be manufactured using methods like 3D printing. When you move from a screen to physical objects, small mistakes become real problems. A hole that is slightly too small won't fit a component. A misaligned feature can make an entire assembly unusable. So today we'll start thinking not just as designers but as engineers. Another important difference from yesterday is that today will be more interactive and analytical. Instead of just following steps, you'll be expected to think about why each step is done, predict what will happen when something changes, identify mistakes, and improve designs. The focus shifts from doing to understanding. You'll also look at how individual features combine into a complete system. A simple sketch or extrusion is simple, but real parts are built from multiple features that depend on each other. Understanding that structure is what allows you to create more complex and functional designs. By the end of this session, the goal for you is not just to know how to create a model. The goal for you is understand how we made that. So think of today as from moving from basic usage to actual design thinking, from drawing shapes to engineering paths. And as we go through this, don't just follow along, pay attention to the decisions being made. Because in real world engineering, the decision matter more than the tools. So let's get started with Onshape. Yesterday, as I said earlier, I introduced the concept of Onshape, like the basic user interface. And today we'll be going into more depth by creating multiple part studios and combining that into an assembly. I'm going to present my screen. Just Mr. Zahal, please let me know if it's visible. Right, can you everyone see my screen?
Of course, Alibay, it's visible, and I hope all the things and all the audience would also be visible too.
Right, okay, thank you. So as you can see here, this is the Onshape basic interface. This is what you get after you've already signed in. Signing into Onshape is completely free, so that's not a concern. I saw that yesterday a lot of you had that concern about what softwares are free, whether you have to pay for any of them, or if there's any subscriptions or anything. But Onshape is completely free, although you can buy some sophisticated libraries, but those are often not necessary. So you can just go on to create and go on to create a document. You can just name this anything. For the purposes of today's session, I'm just going to name it uh, uh, Dabble session here. And it'll just take a while to load up. hmm Now here's the basic CAD interface you get. You've got a 3D model, 3D planes, top, front, uh, b- uh, behind, left, right, and bottom. So yeah, today I'm gonna be showing you guys how to make uh, a a bearing plate with a bearing imported from a library, along with a bearing retention plate. Yeah, with a shaft, which you can use in your robots for the wheels and for other mechanisms that might require rotation. So to start off, you want to make a sketch and select what plane you want to make the sketch in. For the purposes of this session, I'm just going to make it in the top plane, but you got to select the planes according to how you want your robot to be built. Now you can go into sketch one and you have a lot of tools to make a drawing. So the most basic tool is a line, which is what I'm going to use to make a line like this. And so here you can s- select the dimensions of this line, and I'm gonna make this 25 centimeters. Hmm, Okay, and I'm going to make another line over here. Mm, you've got to select your dimensions according to how you want to make things, and you can just create an outline of what you want to make. For example, I'm just gonna make a triangle here. So yeah, that's done. And to make this into a 3D plane, you can just go to this function right here, which is extrude. You can do this by clicking on it, or you could just press Shift T. And now that you've pressed extrude, as you can see, this has become a 3D shape. With this arrow, you can select the height of the shape. See, this arrow is pointing rightwards, it's going like this. And its height can basically be called its depth as well, which you can also type in, which I'd recommend you guys do that because you can select more precise dimensions on that. So I'm just gonna have this be 50 centimeters, and now you have a plate like this, sort of similar to a ram. Mm, uh, Yeah, so you can use CAD to design a lot of different things, and I'll just show you thing we've designed earlier. Let me just load it up real quick. Just give me a second, please. Uh, mm, I'm just opening up the file I'm going to show you guys in a second. Right, I have it. Thank you all so much for waiting. Here. This is the plate you can make. Uh, as you can see, this sketch on this plate it looks very complicated, but it's just a combination of everything I showed you earlier. You just make lines with dimensions. You define these dimensions, you define the diameters of these circles. You can make a circle with either the center point circle tool, or you have multiple kinds of circles, like 3-point circles or ellipses. That all of that just depends on what kind of model you want to make. And I've extruded this shape. Uh, yeah, and after extruding, this shape looks like this. Like it's a 3D model, and its depth and everything is already defined. And this is just one part studio of your entire model. So each different part of your robot is going to be a different part studio, like the wheel, the chassis, the grabber, or whatever game field interacting device you have for your team. It's going to be a different part studio. So this is just a part studio, and this is the bearing retention plate. Now next, I'm going to show you guys, this is the bearing. This is basically where the shaft is gonna go into, and this thing has the same radius as this big hole in the middle. And those two side holes are for like screwing the part in. So yeah, for tools like this, I'd recommend you just import it from an already existing library, which you can download different kinds of libraries on Onshape. Like for our first robotics competition, we have the FRC design deriver, where we can get all parts for FRC very easily on CAD. So yeah, this is very helpful to just derive something like this. And another thing which I've made is this hexagonal shaft, where the first thing I did was just make a hexagonal thing which is round, so I can extrude it later on and it fits into the shaft, into the bearing, sorry. So I've extruded this, and yeah, it's 3D now. So as you can see, this entire thing was made from a 2D hexagon to a 3D shaft. And now assembling all these things, sorry, that's another part studio. Yeah, when you go into assembly, you can interact with all of these part studios differently. You can like move them across. Yeah, so you can move them across. You can control them, and they can rotate along their axes. And yeah, when all of them come together, you can have a rough idea of how your robot or how that one specific mechanism is going to look like. And to add the part studios into the assembly, you go into insert and you select each part studio you want. Like I've inserted part studio 1, part studio 2, part studio 3, and now I've inserted a second version of part studio 3. So now that that's inserted, I can freely move this along how I like. And I can rotate this along the three different axes using these circles. And these arrows can help me move them up or down, like front and back, and right and left. Sorry, I just rotated again. But yeah, that's basically the rough idea of how you can make your robot using CAD. You can find more detailed courses on YouTube very easily. And in fact, FRC Kaizen has some very detailed courses on how you can learn CAD, how you can use it for different purposes. But if I go deeper into that, that's going to take a very long time because learning CAD is something which takes years and years of experience. But learning how to perform basic CAD and how to make like very basic designs is a very easy process. So, does anyone have any questions so far? Mr. Sahil, can you check the chat box for any questions?
Yes, Arvind. Actually, there are no questions in the chat box also, so we can proceed further. And I would like to all ask all the participants and audience to please register on the form so you can get the certificates. You guys
Yes,
can.
registering. Yes, registering and getting the certification for this course is a very important thing because it actually proves that you have the skills that you've learned in this session today. So it's something which gives you more credibility and gives you more confidence as you go forward in your robotics journey. On that note, Darsh, I want to give it over to you. Can you please cover programming now?
Yes. Hi, everyone. We're going to be covering the programming part. As you remember from last session, we're going to be using a software known as PictoBlocks, which is a sort of copy of Scratch, but allows you to connect to Arduino's and any quirky bots. So the I'd like Arabi to please stop sharing your screen. And I'm going to show you the physical bot first, so that you can understand what we're going to be actually coding in our whole robot. So I'll just be showing that to you real quick, right? So we have this bot over here, and inside, so for each wheel, we have one separate one of these motors, right? And so essentially, with PictoBlocks, what we have to do is run each motor. Try, we have to run each motor so that the bot can perform a specific task. Like in this case, our bot is going to be probably moving back and forth, right? So I'm going to open PictoBlocks and I'm going to show you how that's actually done. So I'll just be sharing my screen, and I hope my screen is visible, right? So when you open PictoBlocks after installing it from Google, this is the first screen that you're going to see. So for our purposes, we're going to be selecting the normal blocks, the ages of 7 plus, right? And as soon as you open this, you'll notice that this is the exact copy of Scratch with all the blocks that we know of, right? So so as I explained last session, in basic picture blocks, we have a sprite that moves on the screen, and we use these blocks to actually control it. But since we're going to be controlling our robot, we have to connect to it. So in your Arduino, in the Arduino board, you'll have a USB port which you have to connect to your laptop. And once you've done that, you go to connect on the top, and you select a board, and you select the exact type of board that you have. So for me, I have an Arduino Nano, right? And we're going to select the board type. And as you can see, as I've connected it using the USB port on my laptop, I can see that I have COM11 coming up over here. So I'll just connect to that, right? And as you can see, now that we've done that, we have multiple more sections for all the Arduino stuff. So as you can see, it's talking, there's a pop-up for the firmware which you have to allow to upload, otherwise the code may not work. And and now that we've done that, we're going to move on to actually coding the bot. So you can't code directly like this because, as you can see, the interface is still trying to make you control your sprite. So you have to convert into a mode that will allow you to directly upload your code to the Arduino. So from the top, you select the upload mode over here, which as you can see now shows me a C++ code with the blocks on the side, right? So how this is going to work is that when you're wiring up your Arduino, we have multiple pins that through which you can send a high or low signal, which is basically the equivalent of 0 and 1. And in the specific type of pin, which we call the PWM pin, you send values from 0 to 255, which basically acts as your decimal values between 0 and 1, so that you can set the level at which you want to add power to. So in this, we're going to use the basic event block, which is when the Arduino Nano starts up. And in today's for today, we're going to be running the right side motors of the bot. So as I said, we connect motors to pins on the Arduino, so that when you send a signal to them, you can decide whether the signal will be high or whether it will be low, which basically acts as an on and off switch, right? So in my Arduino board that I have right now, I have the pin configuration to be that the pin 8 will output as a high, and the pin number 9 will output as low, and I have one PWM pin, which is number 10, or sorry, it's number 11, which will output as 200 instead of 255, right? So this on its own, what it's going to do is that as soon as I upload the code from here, it's going to start running those motors, because I'm essentially sending high and low signals to each of the pins, right? So so I'm going to bring this bot right over here. And as you can see, these are the right motors. So these are supposed to spin right now, right? I hope it's visible to everyone. And essentially with the bot, when you have to connect the battery. And as you can see, as soon as I connect the battery, these motors start moving forward, which means that the code is correctly set. I've configured the right pins. And so if I were to put this on the floor, this robot would be rotating towards the left, because I only have my right motors turned on, right? So that's practically it for the programming part. Essentially, in PictoBlocks, you're supposed to be configuring each pin to have a different signal, which is the way you actually control each motor. And since in Codeavour, all your bots, what they're essentially going to do is that you're to perform any task, they are supposed to run a motor. So that's exactly what that's exactly what we're doing over here, right? I'd like to hand it over to Ravi now for the 3D printing section.
All right. Okay. Well, as I mentioned yesterday, we at Kaizen use a 3D printing software. We use a 3D printing software called Cura. So, let me just give you a brief introduction before actually going into the software and its UI. So now that we've designed a part in CAD, the next step is turning it into something we can physically print. But here's something important. When a 3D printer creates an object, it does not usually make it completely solid. Instead, it fills inside with a structured pattern, and that structured pattern is called infill. Infill is the internal structure of a 3D printed object. From the outside, a print may look solid, but from the inside, it contains a repeating pattern that provides strength while saving material and time. This is one of the key advantages of 3D printing. We can control how dense or light an object is. And the infill percentage determines the density of the object. The first parameter is infill percentage, which controls how much material is inside the object. This is usually expressed from 0% to 100%. 0% infill is basically where the object is completely hollow and only the outer walls are printed. This is very fast, uses very less material, but it's very weak and it can like bend very easily. Uh, so this should only be used for visual models or having decorative parts. The next is 10 to 20% infill, which is the most common range. It is very lightweight, reasonably fast to print, and it has enough strength for very basic uses. It's fine for something like a prototype or very basic models or non-loading bearing parts. This is basically the default in most slicer softwares. 30 to 50% infill is where you get significantly more strength. It is way more durable, it is more resistant to bending, and it has a way longer print time. This is used for functional parts such as spacers or shaft collars. Mechanical components under moderate stress are a place where these could be used. 60 to 80% infill is very high strength and it approaches actually being solid. It is very strong but and it's quite heavy and it takes a much longer time to print because obviously there's way more filament being used. It is used when what's it is used when strength is critical to the usage of the function, to the like part. When a part is 100% infill, it is completely solid and it has the maximum strength. It has the most material usage and it has the longest print time because it's completely filled out with the filament and yeah, it uses the most amount of filament. In most cases, well-defined infill patterns can achieve similar strength with less materials, so you almost never go 100% infill. A key trade-off with infill percentage is these things. As infill percentage increases, the strength of the material increases, the number of hours for the material to be printed, and how much material is going to be used. So increasing infill makes parts stronger, but also makes printing slower and more expensive to produce. Now we're going to move on to infill patterns, which, as I described earlier, different infill patterns help with different use cases of the 3D printed parts. So the first is a grid pattern, which is just a simple square pattern, and it prints very quickly, and it provides very basic strength and turgidity to the part. The next is a lines pattern, which is just some straight parallel lines. It is very fast to make, and it's weak under some conditions. Uh, Printing it under like keeping the part like this, where the lines are vertical is going to lead to the part being stronger, but obviously when it's like this, the part's going to be much weaker. Having a triangular pattern is stronger than a grid pattern and it has better load distribution, but it takes slightly longer. It is used when structural strength is needed and material is not that available. A honeycomb pattern is a hexagonal structure which is strong and efficient and is good at distributing forces. It is used when balance and material use are required. A gyroid pattern is a complex 3D continuous structure with strength in multiple directions and no sharp directional weakness. It is a very popular model in modern 3D printing and provides excellent strength to weight ratio, but it takes a very long time to print. A cubic pattern is a 3D repeating cube structure where it's strong in all directions and it's good for functional parts. It is used when uniform strength is required, and this takes a moderate amount of time to print. Directional strength is something that is very important when it comes to 3D printed parts. When parts are presented from, when pressure is applied to parts from multiple directions, the forces act on them differently. They compress differently and they turgid to a different extent. Lines patterns are weak sideways, grids are stronger but still directional. Gyroid and cubic are the most reliable under all directions. So choosing the right infill depends very heavily on what kind of a part you all are printing. If it's a decorative model, then you can go for a low infill and a very simple pattern. And if it's a prototype, you should go with a medium infill with something that prints very quickly. And a functional part should probably use a higher infill with a stronger pattern, probably a cubic or a gyroid pattern. There's no single best infill percentage or infill pattern. It all depends on what you require. Real world engineering actually uses infill to optimize its material usage. Instead of making everything solid, engineers design internal structures that reduce weight, maintain strength, and improve efficiency. This concept is not just used in 3D printing, but in aerospace, automotive designing, architecture, and of course, robotics competition robots. Infill determines how a 3D printed object behaves internally, and it's controlled by the density, which is affected by the percentage of the infill and the infill pattern being used, which decides the overall structure. By adjusting these, we can control the strength, weight, and print time of the object. Understanding infill is essential for moving from simple models to functional real-world parts. Now, I'm just going to run the program for this and show you guys the user interface of Cura. Till I have that fired up and connected with my 3D printer. Darsh, would you mind taking over for the assembly part, the presentation?
Yes. So for assembly, how we're gonna go about this is that so in assembly, essentially, what we're doing is, as I mentioned yesterday, we have to make sure that each part is well aligned and it actually works with the rest of the parts that you've made. Because if there's any deviation in that, it can end up breaking your board. It might cause problems in the motion. It's not gonna be well structured. Right, so I'm going to be showing you a bot again, right, which is where we have a lot of screwing, a lot of plates on it. So I'm going to hold up our bot like this so that you all can see it, and I'm going to explain how it's done. So these two rods are essentially a grabber. So we use these to grab any part of any ball, any parts in the field. And how this is essentially done is that, as you can see, we have screws over here and 3D printed gears which allow for only one motor to be controlling both of these arms at the same time, right? And so how the assembly process works with this is that we first check whether the screw is actually compatible with the hole that we've made on the gears, and whether it's compatible with the whole body as well, because we don't want a screw which is incompatible, so that such that if anything, if maybe the gears rotate too fast, the screw might snap out of place, and that can really hurt anybody that it collides on, which is just not that great, right? um and so even for these arms, so we use a CNC machine to cut metal, right? So that we can actually so, so that we can get the exact shape, the exact dimensions that we want. Even for these, to be able to connect it to the gears, which are these two small screws over here, we need to check whether the screw length is okay, so that nothing, so that, it's almost flush, but not too flush, and not extruding too much outwards, right? And so with that, we're able to make this grabber, and so that we can pick up any object, we can move it anywhere on the field, right? That's essentially how an assembly works. It's a lot of screwing, it's a lot of putting together, and also checking what whether the parts that you've made, are they actually compatible, right? And so with that, uh, uh, this basically concludes the whole session. So as you've seen today, we dive deep into CAD, into programming, into 3D printing, and how assembly actually works, and as I've shown you, how it's shown you a live example on how it's actually working, right? I'd like to hand over the mic to Aravir.
Right, okay. Now I'm going to be showing you guys the actual platform of Cura. So let me just present the screen. Just give me 1 second. Mm, yeah, there. And yeah, is my screen visible to all of you? Okay. Now, this is the basic UI of uh, our Cura Ultimaker, and this is just like a pre-recording of something we did previously. So you got to select a computer. This is going to show you all of these screens, and you got to sign in, obviously. So I'm just going to skip that for now and show you guys. Now you have to add a printer. So you select whatever kind of printer you have, and these are the two different kinds of printers, and you can just search up local printers using Wi-Fi or Bluetooth, as I mentioned earlier, or you could just connect them with uh, USB. So these are all the printers that I've connected previously with my laptop. So yeah, and I'm just gonna be selecting a printer with this. Just give me a second. Mm, just let me skip forward a bit, or this is unnecessary. Now here, uh, let me go back. Let me go back. Now here's the machine settings. I can just decide what the printer settings are going to be, what are the X and Y axis dimensions of my drawing, and like of my STR file, and what are the print load settings and everything. And yeah, so So other than the machine settings, next you can see what all updates Cura has had, which is not necessary. So this is how it's going to look like. It says ender down here for now, but really depends on what kind of a printer you have and what the base plate of that printer. Ooh, what's that error? Okay, that's probably nothing. But the base plate is going to look different for every single 3D printing model you've used. And this grid pattern is going to have different dimensions according to what dimension you defined earlier. So this is basically the basic UI of what the 3D printer looks like. You can drag it around, you can change your view, and basically just see how the model is going to look like before you actually 3D print it. So here you can define a bunch of things. You can change the printer settings here again in case you made a mistake earlier. You can move the entire thing around from here as well. So yeah, here I've added a basic STR file of a CAD model made earlier from from Onshape. So you just download that CAD file, and there's multiple STR file converters you can find online or download. We personally like to use an online one because it's just way more convenient. So once we have the STR file, we can upload it into Cura, and here we can change a few things here. Like as you can see, we can change the infill percentages, we can change some of the dimensions. We also have to change. We're gonna have a low infill percentage for this because obviously this is gonna be a decorative part. We're not gonna be able to use this in any robot. And as you can see, I've increased the size of this object, and I can move this within the three axes, and as you can see here. So you can make a lot of different changes to how this thing works. Here I've changed the filament material I'm going to use for this, which is a setting which is only available in some 3D printers, not all of them. Most 3D printers usually have one filament you can put in, and the other filaments you just gotta uh, select individually, like manually. You can't select them on the software. You gotta just take them out and plug them in manually. So yeah, here I can change some parts like I can see how it's gonna look like, how the cross section is gonna look like. And this little tab is how you can adjust the strength, you can adjust the infill density and the infill patterns here. As you can see, the infill density is gonna be low because again, this is a decorational piece. So as you can see, a grid pattern is being used here. It's a very simple thing. It's going to print very quickly. Now it's gonna be a lightning pattern which I didn't cover, but it is another very helpful pattern which also gives you like multi-directional stability. So yeah, you can customize a lot of things here. This is like an entire rabbit hole of very detailed things which I obviously can't go over for the purposes of this session, or else it'll be multiple hours long. but we do have courses on 3D printing made by Kaizen available, as well as many different good quality courses on YouTube. So yeah, you can just change all these things. You have a lot of parameters you can put in before uh, actually printing the thing. And you can edit these parameters in Cura itself, or you can have them edited in the STR file before. So yeah, that's pretty much it for 3D printing. That's all the details we're gonna be going over today. So yeah, thank you so much for paying attention. And does anyone have any questions?
In the chat box, I cannot get any more questions right here.
All
So,
right.
is there anything we can do for the audience?
The what the audience can do is they can go to the link in the description of this live and they can sign up for the session. Like sign up for the session, register for it, and they'll get a scaling certificate, which is basically a certificate that says you've learned all this and possess these skills, which really helps with your confidence and really helps with your credibility, which is something which is very important to us because over the past two sessions, you've seen how ideas turn into real things. You started with nothing, just a concept, and then you learned how to design it using CAD. You defined dimensions, shapes, and structure using it. And after that, you saw how those designs can be manufactured using 3D printing. You also learned that something as simple as the inside of a print, like infill, involves decisions about strength, efficiency, and performance. You also learned how these individual parts can be assembled together to make a cohesive robot, and how this robot can be programmed using something as simple as pictoblocks to run properly, as I showed you earlier. But here's the important part. None of this matters if you don't use it. CAD, 3D printing, programming, or assembly robot are just tools for robotics. Knowing how to use the tools is useful, but what actually matters is what you choose to build with them. Right now, you have the ability to take an idea and make it real. That's not something most people can do. Most people stop at thinking, but you know how to move beyond that. When you start building things, you'll notice something quickly. Your first designs won't be perfect, they might break, they might fail, or they might not work the way you expected. That's normal, that's part of the process. What matters is you move forward, you improve, each design gets better, each mistake teaches you something, and each iteration brings you closer to something that actually works. If you keep going, you won't just learn how to use software, you learn how to think differently. You'll start seeing problems as things that can be solved. You'll start to ask, how can I design this better? How can I make this thing work? And that's the real skill. So don't stop at what you learned here. Use it, build something simple, then improve on it and build something better. Then continue this process until you build something that actually solves a problem and build something that actually works in the Codeavour competition and something that can actually win. Because at the end of the day, this isn't about teaching you about CAD, robotics, about 3D printers, about programming, or teaching you about assembly. It's about turning your ideas into reality, which is the philosophy that Kaizen believes in, and which is what we believe engineering is all about. So now you know how to start with your robotics competition journey. And thank you so much for having us as on behalf of Team Kaizen. Thank you so much, Mr. Sahil. And now finally, I want to hand it over to you, Mr. Sahil. Thank you so much.
Thank you, Aravind. And there's a one more question I would like to ask Josh if we can show how to change the modes from the stage mode to upload mode because so many guys are asking about that. So can you please share your screen with this?
Yes, I'll show how to uh, I'll answer this question right now. So, uh, the way to change between these modes is from the top over here. I hope my cursor is visible, right, on my screen. On the top, by default you'll be in stage mode, right, which is where you'll see your sprite and all. From here, you go to upload mode, which will then show you an interface of the C++ code that is made by PictoBlocks. after you put in the these blocks over here, right? And then when you've done that, you have to upload the code from here. And if your battery is connected to the bot, you'll see that automatically as soon as you upload the code, within a few seconds, the motors will actually start running if you use this code. I hope that answers the doubt.
No, there are no other doubts. Uh, and one more thing is there that can we simulate animation in Onshape? One question is there.
Yes, you can simulate animation, but not in the traditional sense. You can have the different part studios moving around with different assemblies moving around together. And yeah, it's just a very complicated process. You'll have to learn a lot of CAD for that, which is something that we haven't personally done. But you can use tools such as revolute, rotate, and like linear uh, mates to like make that easier, because doing it on Onshape is going to be way more difficult than doing it on some of these platforms. So yeah, if I hope your answer is like, I hope your question's answered. You can make an animation on Onshape, but it's just not very practical and not something that I would recommend. But if you do want to do it on Onshape only, then yeah, you can do it.
Thank you, Aravi, for the answers. And there's no answers, and I guess these two bootcamp is successful for the audience as well. The bootcamp and for the team also, Team Kaizen at Jai Shri Perival International School. Thank you, guys, for hosting the bootcamp. By finishing this final session, audience is so much closer to understanding how to design, build, and control a dependable, competition-ready robot. So, okay, one more question is there: how to open the designing part in Onshape? When I open it, only shows the about, and someone is doing it in iPhone. Can we do it in iPhone, Aravind?
I'm not sure if you can do it on iPhone, but even if you can, I really don't recommend doing it on iPhone. Just use Onshape on your laptop or any sort of desktop you have. Anything with the mouse is fine. I really recommend not using Onshape on an iPhone, but of course, you probably can use like the Onshape app.
Okay, so I guess the person who have asked this question get answered. So there are no more questions coming along. So thank you guys for hosting the sessions and thank you for the joining. I hope this inspire you to keep experimenting, iterating, and building the better robots in the future. Thank you everyone for
Thank you
joining
so much.
and
Thank you so much on behalf of guys and Mr. Sahil. Thank you everyone for joining the session. We recommend you again to register using the link in the description and proving your skills in the Codeavour competition. We look forward to your performances. We'll be there watching, and best of luck. Yeah, thank you.
don't worry guys, I have added